Okay, so today our learning goal says, I can use substitution, and we've actually been doing some of this already, and replace variables with values. So substitution is replacing a what then? With a number value? What are we going to replace? What are we going to replace? It says it right here in the learning goal, a variable with a number value. So when we substitute, we're putting in a number value in place of that variable, whichever one will make it true or whichever one we're told to substitute in. So in our equation, x times 4 equals 24, what is the only number value that can be substituted for x to make that statement true? What would it be? What times 4 equals 24? 6. Or in other words, what can we think in that particular situation? What do we have to think? Not only what times 4 is 24, but what if you can't answer that? What could you do? You could divide. What would you divide? You know, it wouldn't be 4 divided by 24. Danny? It would be 24 divided. Let's write that up here. Think 24 divided by 4 equal, or by 6, or excuse me, then I put the 6 there. I meant the 4. Okay, so 24 divided by 4 equals 6, right? So x equals 6. It is the only number value that makes that statement true. Unless you can think of another one. Can you think of another number value that makes that statement true? Anyone? Okay, let's go to page 58 in your workbooks. Go to page 58 in your workbooks, to the Apply Skills page. Our directions ask us to substitute the value for the variable that makes each statement true. So what value would make the statement x plus 12 equals 17 true if we substituted that value in for x? Caden?
5 plus 12.
So 5, because 5 plus 12 equals 17, right? Okay. What could we think in that case? What if we don't just know what added to 12 gives you 17? Or in other words, really, what does your brain really have to process? Sam?
17 minus 12.
Yeah, 17 take away 12, that gives us 5. So if 5 and 12 were added together, it should take us back to 17, shouldn't it? Okay, how about number 2? What would be the value of a in our a times 7 equals 56? Harley? 8. Okay, so Harley is saying then that 8 times 7 should equal 56. Is that true, class? Okay, again, what could we think in this case? What could we process to help us get that 8? Kira?
56 divided by 7.
56 divided by 7 is what? How many times can you take 7 out of 56? You can take it out 8 times. Okay. How about number 3? What is the value of b in this one? 45 divided by 9 equals b. Well, this one we think just exactly what it says. How many times can you take 9 out of 45? 5 times. b equals 5. So 45 divided by 9. There are 5 9s in 45. Okay, you go ahead and finish the last 4, and let's see what we all get. Okay, and I want you to write something down. I want just the answer, either the process you're using to get it, or the substitution to show that it is really going to make it true. Get an answer for each of them, please. a bunch of white space off to the side over there if you have to do some work over there, so that you don't use your calculators. Just go show you work off to the side if you need to. All kinds of white space on that page. Okay, let's start going through them. Number 4, what is the value of z in our statement 27 minus z equals 18? Ikea? 9, Ikea says. Okay, so what was your process, Ikea, that helped you get that? What did you do?
Subtracted 27 with 18.
I think you probably did it the other way around. You took 27 and subtracted 18. Order matters in subtraction. So 27 take away the 18, that leaves us 9. So in other words, if we take 9 away from 27, it should result in getting 18. Okay, that's the correct answer. How about number 5? What is the value of w in 39 plus 47? Well, that one we just basically add them together, don't we? Sylvia? 86, she says. So in other words, if we added 39 to 47, we should really, truly get 86. Okay? Anybody know a shortcut to adding that where you wouldn't have to go over here off to the side and do this? Other than your calculator, that's kind of a nice shortcut too. What if you didn't want to have to go through all that? Anybody know a quick shortcut for adding those two numbers together? Got one, Sylvia? Well, now you're doing the algorithm that says add the ones together and then carry and all that. What's 39 really close to, class? It's a nice kind of round number. 40. So could you add 40 to 47 in your head pretty easily? What is 40 plus 47?
87.
87. But we jumped up 1 to get to 40, didn't we? So now we got to take that 1 away. What's 87 take away 1? 86. So see, we can function without calculators also. Okay? How about number 6? What is the value of d in d minus 25 equals 25? Caden?
25.
25? So in other words, if we substitute 25 in for d, we get, after we subtract 25 from it, we have 25 left over. Is that true? 25 take away 25, is that 25? No. So what's it going to be instead, Hannah?
50.
50, Hannah says. Okay, so let's try 50 instead then. If we substitute 50 in for d instead, 50 take away 25, does that give us 25? It does, doesn't it? Yeah. It's kind of throw you off one, wasn't it? Okay, how about number 7? What is the value of y if we're going to take y times 5 and get 35? Tyler? 7. So let's try it. Is 5 times 7 35? It is, isn't it? Okay, so substituting. Now, notice something about every single one of these problems along with that one we did on our note page. Are there any other number values that would have made any of these true? Or do they only have that one that we found for each of them? What do you think? Are there any other number values that would have worked? No, there's only one. Okay, there's only one. So some equations only have one number value that will make that equation true. Okay, let's go back to our notes page. So set your workbook aside for now. Okay, we're on the part right here where it says we can also use substitution to find specific cases of general patterns. We've already done some work with this, and general patterns are a big thing for us to recognize in math that we can say we can count on these all the time. So here they're having us substitute the given values, in m plus 0 equals m. So our first given value is m equals 3. So we're going to substitute 3 in for m in both spots. Go ahead, do this on your notes, please. We're going to substitute 3 in for m in both spots. And then we're going to do some evaluating here. We're gonna clean this up. What's 3 plus 0 on the left side? It's what? 3. Okay, and then of course there's nothing to do on the other side. It's already nothing to add or subtract or multiply or divide or. So 3 equals 3. True or false?
True.
Okay, that's true. So the value m, when it's equal to 3, made that equation true. Is that the only one then? So how about when m is negative? Let's try a negative number. What if we have negative 1 4/10 for m? So we substituted in both spots where m is. What's negative 1 4/10 plus 0? Negative 1 4/10. Negative 1 4/10 is equal to negative 1 4/10. True or false? True. They are the same value. So now how many values do we have for m that make this equation true? How many do we have so far? 2. Yeah, we got 3 and negative 1 4/10. We tried a positive, we tried a negative. Well, let's try a fraction. Let's see if maybe a fraction will throw it off. So we have 1/2 plus 0 equal to 1/2. 1/2 goes in both locations for m. Well, what's a half plus 0? 1/2. So we end up with 1/2 equals 1/2. True or false? True. Okay, we're up to how many values now? Now we're up to 3 values. How many more do you think there are? How long do you think we could keep picking values for m, other values for m, and it would maybe make this equation true? No more? Just the 3 that they chose for us? Just those 3? Really? Are you sure? Because what's the pattern that's going on here? What's happening in this particular equation? What is the pattern? Find it. What's the general pattern that's going on? Because typically, if there's this many that make it true, we've already found 3, there's probably a pattern going on. What is it? Sam?
0.
Okay, what about the 0? What are we doing every time with the 0? What are we doing every time with the 0, Sam?
Subtracting. Oh, adding.
We're adding 0 every time to the value that we're substituting in, aren't we? So we're subbing in a value, adding 0 to it, and what happens every time? We get the same number. We get the number that we subbed in, don't we? They made it true every time. Can you think of any numbers that wouldn't happen? Maybe we should think of it that way. Can you think of any numbers that if you added 0 to it, you wouldn't end up with that same number? I don't think there are any. Do you? Do you think you can ever change a number's value by adding 0 to it? No, you can't. So therefore, there is a more than one value. We would say, therefore, there is more than one value. Therefore, there is more than one value for the variable m that makes the equation true. We've already talked about this pattern. We've already talked about this pattern. When you add 0 to a number, it does not change the number, does it? It does not change it. So there's a case where there are several different values for the variable that would make the equation true. Okay, let's try this one then. Substitute the given values in x minus y equals y minus x. Let's underline that. Substitute the given values into the equation x minus y equals y minus x. We have 2 different variables involved here. So when x is 4 and y is 2, so 4 is going in for x, 2 is going in for y. y minus x, that would have changed their order around to 2 minus 4. What's 4 minus 2? 2. What's 2 minus 4? Negative 2. Because remember, what are we going to do with subtraction when we are subtracting a bigger number? We're going to take it and change it to add the opposite. So that becomes negative 2. Not 2, does it? It becomes negative 2. So the one side is a positive 2, the other side is a negative 2. Is that true or is that false? 2 equals negative 2. False or true or false? 2 equals negative 2. Is 2 the same as negative 2, in other words? No. Having $2 in your pocket is not the same as owing somebody $2, is it? No. So this is false. Write a false there. We're going to go like this. We're going to say it does not equal, actually. Except when we put that there, our false doesn't look very good. You know what? I'm going to undo that. We're just going to leave it like that. Okay, let's try another one then. Let's see if this, maybe it works with when zero's involved. You know, zeros sometimes is kind of that friendly number. Let's try with 0 then. 0 for x, 3 for y, 3 for y, take away x, or 0. Well, what happens when you start at 0 and you take away 3? Where do you end up on the number line? At negative 3. Or in other words, remember, this can be changed to add the opposite. And 0 plus a negative 3 is negative 3. How about the other side? 3 take away nothing. 3 take away 0. You get 3. Because even if we change this to add the opposite, what's the opposite of 0? 0. It's itself. So we could just change this to 3 plus 0. What's 3 plus 0? Still 3, isn't it? Okay? So, tell me, did we end up with a true statement? Is negative 3 equal to 3? No. This is what then? False? Yeah, this is false. Therefore, we found a general pattern when we add 0 to a variable, we get the variable itself. But when we change the order in subtraction, that's what's going on here, we're changing the order. When we change the order in subtraction, that's a no-no because it creates a problem. We end up with false statements. So this is not a general pattern. We cannot reverse the order. That's why every time you guys say something to me like 18 take away 25, I say to you, I think you mean 25 take away 18 because they mean different things. So let's put that little note here. Order matters. You have room? Or is there no room down there? Okay, there's a little. Order matters in subtraction. This is a big deal for us to remember. Subtraction is not commutative like addition is. Order matters in subtraction. That's what we just discovered there. So questions at all? You'll be doing some of this kind of stuff in your homework. All right? Mm-hmm. Okay, let's go to the back then. Proportions. A proportion, we are going to be, we've actually kind of been somewhat working with them already and just not realizing it when we've been working with our tables. A proportion is one ratio equivalent, this is kind of a big word, spell it nicely, equivalent to another ratio. One ratio equivalent to, or in other words, equal to, the same as, it really is the same value as another ratio. And what do we know about ratios? They are a what? They are a comparison of two numbers where what matters? Where order matters. Okay, so if we have a ratio set equal to another ratio, we call it a what? One ratio equivalent to another ratio, what is it? A proportion, that's what we just wrote. A proportion is one ratio equivalent to another ratio. So from the following table, set up some proportions. Okay, look at, I've set one up for us. Okay, here's our first one. From this table, I took 1/3, this ratio right here, and I set it equal to this ratio. And then we're going to decide if it's really true or not. In other words, is 1/3 equivalent to 2/6? Well, if I take the numerator up here and multiply it by 3, I get the denominator 3. Well, then that should happen on the other side also. If I take 2, the numerator, and times it times 3, I better get the 6 that is there. Or I could work from the basement up, I could do 5. This is called our vertical strategy. What is happening as we go from the upper floor to the bottom floor to the upper floor. Okay, give me another proportion you think we could set up from this table showing us sugar in cups and flour in cups. No, give me another proportion. One ratio equivalent to another. Kagan?
2/6 and 4/12.
2/6 and 4/12. So 2/6 equals 4/12. So in other words, if I took that 2/6 I could get from 2 to 6 by doing what again? Multiplying by 3. I could get from 4 to 12, multiplying by 3. So remember in our table, the same thing should work all the way across the table. Or if I want to work from the bottom floor up, what do I have to do to 6 to get 2? Divide by 3. What do I have to do to get from 12 to 4? Divide by 3. So is this a true proportion? Absolutely. Jaden picked another proportion from that table. One ratio that really means the same as another. So this is what they were doing in your homework for today. In those 3 problems that had happened that you had a different ratio name for the one, but the answer key than what the answer key had, they were really equivalent to each other. One had just been renamed, like in this table, what is the simplest form of the ratio, the simplest form that we could talk about the comparison of sugar to flour in that table? What's the simplest form we could talk about of comparing the sugar to the flour in that table? Simplest form. Okay, 1/3. 1 cup of sugar for every, how many cups of flour? 3 cups of flour. That is the simplest form, but it really means the same thing as for every 2 cups of sugar, there are 6 cups of flour. And that having 2 cups of sugar to 6 cups of flour really means the same thing as having 4 cups of sugar to 12 cups of flour. Somebody give me another proportion we could set up in this table. Let's have another one. Cheyenne?
1/3 to 5.
Okay, 1/3 equals 5/15. There's another one. Somebody give me another one yet. Give me another one. Somebody who hasn't yet. Somebody who hasn't talked yet. Let's check out your vocal cords. Oh, wait, I haven't heard from you, I don't think yet.
1/3 and 3/9.
1/3 equals 3/9. There's another proportion. Kira?
2/6 equals 3/9.
2/6 equals 3/9. You think we can do this for a while?
Yeah.
I bet there's a few, maybe a couple more that it could still even be set up. So one ratio equivalent to another ratio. It's important that we start understanding that that makes up a what? Proportion. Okay. Well, the reason that that is so handy is that all of those can be written is because what if we didn't want to have to extend a table? What if we didn't want to even have to make the table very far out at all? So let's not extend this table to find how many cups of flour, let's underline this, how many cups of flour would be needed if 9 cups of sugar were used? How many cups of flour would be needed if 9 cups of sugar were used? Okay? So is there, in our table right now, is there a 9 cups of sugar? Look at our table. Is there a 9 cups of sugar in there? No, and we don't want to have to do that. So we're going to take one of those ratios from the table. You get to pick. Which one do you want? The first one, the simplest one, 1 to 3? Okay, let's do 1 to 3. And sugar's upstairs, right? Sugar, and this is flour downstairs. So we have to, in our other ratio, in our other comparison, we have to make sure order matters. So where's the 9 gonna go in our other ratio? Up or down? 9 cups of sugar, we're looking for how much flour there is. Where can we put that 9? Up or down? Sugar. Here? Up. The sugar is upstairs. The sugar is going to stay upstairs. 9 cups of sugar. And what's going to go downstairs? Well, we're looking for flour, so we're going to call it X. We don't know. Okay? So sugar up, flour down, flour down. Okay, now we're going to do our vertical strategy. We're going to say, what do we have to do to get, we need downstairs, so we got to go down. We're going to do something to 9 to get X. So what do we have to do over here? What do we have to do here to get from 1 to 3? Multiply by 3. So if we multiply that side by 3, we can also multiply the other side by 3. So what's going to happen here is we're going to have 9 times 3 should give us our X. So what's 9 times 3? 27. So what did we just find? What's that? 27 what? It said how many cups of flour? Cups of flour. We just found it without extending our table. We could extend our table. We could have gone 6, 7, 8, 9, and we could have kept going up by 3 in the bottom row, but we didn't have to. We used the proportion model to help us get it. Okay, questions?